Hi, in this video I'll be talking about how to solve the heat conduction equation using finite difference method. So this is heat conduction equation, the second order differential equation. T is a temperature, X is a position, H is the heat transfer coefficient, D is the rod diameter, kappa is the thermal conductivity, and T sub A is the air temperature. So these are all known, and the T, the capital T, is unknown. We look for as a function of X. Given that we have two boundary conditions, the temperature on the left is T0 and temperature, and the flux on the right is 0. So dt dx at x equal 1 equal to 0. We use the central difference method to discretize the left side of this differential equation. So if you look at page 83, you find that the central difference applied to this term is going to be ti minus 1 minus 2ti plus ti plus 1 divided by del x squared. All the temperatures are unknown, so we move all the ti plus 1, ti minus 1 to the left, and everything else to the right. And by doing that, we get equation 1 here, where we call the coefficient of ti as b, as you can see here. And what's left over on the right, we call it c, which is a known. So the parameters or the constants b and c both are known. The unknowns are the temperatures or the ti's. So basically, generic form of equation 1 is going to be equation 2, where b and c are the constant we looked at before. Now we can go ahead and set I equal 1, 2, 3, all the way to basically the last point. So imagine we discretize our x-axis to 5 intervals of 0.2. The first point we call it T0, which is given the boundary condition. All other ones, T1 all the way to T5. So now by substituting I equal 1 to 4, we generate 4 equations through equation 2. Now for the boundary condition, we know that T0 is given. For the right boundary condition, we have to discretize the first derivative. Remember, the boundary condition on the right is the flux equal to 0. If you look at page 83 and use backward one-sided difference to discretize this, we get the equation like that, which is equal to 0. And then you can multiply through by 2 del x, and so you get equation 4. So now we have 4 equations in equation set 3, and then 1 equation in equation 4. So total we have 5 equations. We can put them together and create a matrix. So here are the 5 equations. So the 4 coming from set 3, and then the last one is a boundary condition through the no flux the no flux boundary condition. So if you put them together, we get basically these 5 equations. Now note that for the first one, I move T0 to the right because T0 is the temperature on the left, which is given. I don't want T0 to be in the set of unknowns on the left, so I move it to the right, and you get that one. All other ones are basically they haven't changed. All right, so I put these 5 equations into a matrix form, and I get this. So you get a 3-diagonal matrix. On the super diagonal and subdiagonal, you get 1, and on the diagonal, you get minus b. The last equation is different from other ones because the last equation, if you go back to the set, you see that the last equation is coming from the no flux boundary condition and it's different. So that's why you get minus 1, minus 4, and 3 on the last row here. Anyway, so the T1 to T5 are unknowns. On the right side, you get these just by looking at this set. So you get the right side as these numbers or coefficients. And so now you can go ahead and solve this system using syslin. So this is basically solving a second order differential equation using finite difference with one temperature or one fixed boundary on, let's say, left end, and no flux or the derivative boundary condition on the right. Now imagine instead of having one temperature on the left and one derivative of temperature on the right, we have temperature fixed on the two ends. So we don't have a no flux boundary condition. Okay, so now in this case, I'm going to set T1 equal to 0. That means the temperature on the right now is 0. Okay, so in that case, we go back to our equations. And so basically you can rewrite these 4 equations knowing that T0 and T5 both are known now. So T0 is the temperature on the left, T5 is the temperature on the right. So you have 4 equations and 4 unknowns from T1 to T4. These 2 T's are known, all right? And so that's why in this set, I move T0 from left to the right, and I set T5 to 0 because I know that's the boundary condition. So now overall, you get 4 equations and 4 unknowns. You set it up, you get a 3-diagonal matrix. The sub-diagonal and super-diagonal all are 1, and the diagonal is minus b. All right? Now the right side is basically, you can copy from here. That's the right side. Again, you can go ahead and use syslin to solve the system. All right. Now let's look at how we can implement this in spreadsheet. So here's my spreadsheet. First, we look at a problem with 2 fixed boundaries and the 2 ends. Okay, so I have all the parameters h, d, kappa. I calculate for h over d kappa, the temperature, the air temperature TA. The number of unknowns, I set actually my dx 2.1, so if you count that, you see that there are 9 unknowns along the x-axis. The first point, which is the temperature at x equals 0, is known, so that's why we have 9. We have 10 points, but 9 temperature are unknown. All right, now we have b and c coefficient exactly as we had in the notes. And so what we do is basically we go ahead and put these numbers right into here, and you see that the ones and the super diagonal, sub-diagonal are all here, and on the diagonal get minus b, which is minus this guy. You see that? So it's all over here. And now the last equation here is okay. So now actually I'm doing the 2 end boundary conditions. So the last equation should be this one. Okay, so it's 0, 0, 1 minus b, well, depending on how many unknowns we have, but the last 2 elements are non-zero. So we get 1 and minus b, and that's why you have 1 here and minus b there. All right, so this is the coefficient matrix. Now the right side, which is the constant vector on the right side of the equation, is going to be basically this. So it's minus c all over with the minus T0 on the first element. So that's why we have minus c all over here. So this is c and this is minus c. The first one is minus c minus 100, which is the temperature on the left end. All right, so you can go ahead and do the syslin to solve this system. You get the unknowns from here to here, excluding the 2 boundaries, because the 2 boundaries are given. So we should not solve for the 2 ends, right? So when you do the syslin, make sure you highlight from here to here. These 2 ends are manually put in. Now you can go ahead and plot the solution as a function of x over here. So this is going to be our temperature distribution, which is 100 on the left, 0 on the right, and that's how it goes. Now let's move on to see how we can use this finite difference method to do the problem with no flux boundary condition. So this is the setup, pretty much similar to the 2 end boundary conditions. The difference is the coefficient matrix. So remember, this is the coefficient matrix for the no flux. It's minus b throughout except the last row, where you get 1, minus 4, and 3, and that's why we have 1, minus 4, and 3 over here. Okay, the rest is pretty much similar to the 2 end boundary condition. Now on the right side, you get basically similar. The only thing is the last element is 0, and that's why the last element here is 0. All other ones are negative c, so this is the c, you get negative c here, and the first one is negative c minus T0, and that's why I have negative c minus T0 here. You can go ahead and solve this system using syslin. Make sure the unknowns are from the second point right here all the way to here. We do not include the first one because the first one is given, it's 100, you manually put in there. After you do the syslin, now you have the temperatures. You can plot the temperatures as a function of x. You can see this curve, and we see that we impose the boundary conditions properly. The temperature on the left is 100, and the slope, which is the derivative here, is 0. It's flat, right? So the curve is flat, the slope is 0, means the flux is 0, and that is exactly the boundary condition we impose on the right. So hopefully you can use this video to solve the 2 homework problems in chapter 6. The only difference with the homework problems is that the differential equation is different, but overall it's the same. You have the second order differential equation for the reactions in the homework problem. Here you have the temperature or the heat conduction. Other than the coefficients, I would say everything else is the same. So we can use this as a template to solve the 2 problems. All right, so hopefully this is useful for you guys.